so I will also take out the notebook and then we'll continue with our discussion on the addition polymers. Okay. So still remember what addition polymer is? Addition polymer is formed by which type of monomer?
Monomers.
Which type of monomer? What do these monomer have?
They have
And they are alkenes. They are alkenes with CC double bond, right? So today we'll fill on that. So we'll fill on that. Okay.
When you get to the hard stuff before this year.
So just a moment.
He actually asked temperature.
It's cooking.
We're gonna have a test next week.
Yeah, we will have the test after we are done with organic. And we are wrapping up organic today. Okay.
Yeah.
Yeah, great. So, go back to. Okay. So, last time we were right. Yeah. So this is where we stopped. Okay, we stopped at polyethylene. Okay, and we said there are two types of polyethylene. One is called the low density polyethylene. The other is high density. What does that mean? When you look at food wrap or plastic bag, you see they are pretty soft to the touch. But then for plastic chair or plastic stool or drinking cups, these are really firm to the touch. So why is there a difference? What if I tell you that they are both polyethylene? Yeah, you will be hard pressed. Okay, to believe that they are both polyethylene despite them looking very different. One is very soft, and one is more rigid. So how can one soft, one rigid material both be made from the same substance for polyethylene? That's because of the way the polyethylene fibers they are arranged. Can you see that this polymer here, it has a subscript N? That means the real molecule polyethylene is actually something that looks like this. So it's very long. But you don't have to copy this. Okay, it's just to give you an idea of how long it is. So you have a very long chain of like these CH2 units, like are connected to one another. And depending on how these polyethylene fiber is arranged, we can end up getting two very different structures. So you can say this will simplify into this, which will in turn simplify into this. Okay, when we look at the polymer fiber in plastic bag, we find that these fibers they are in a mess. Okay, yeah, they do not line up in a very ordered way. Okay, it's highly disordered. It's because these chains of polymer they are not lining up straight next to one another. This is why they are pretty soft. Okay, as a structure you see, it's not really an organized structure. The intermolecular force between the molecules cannot hold them too tightly together because of the disorderness. It is because of that they are soft. So write down why they are soft. Soft because of the highly disorganized structure. So highly disorganized structure, which means the intermolecular force cannot form effectively. Okay, so intermolecular force cannot form effectively. But when you look at high density polyethylene, the term high density tells you that they are closely packed. That's because inside a plastic cup, you see regions, okay, with very high level of order. Okay, so very high level of order there. Okay, okay. So and that would explain why they are rigid. So they are rigid because they are more ordered. Okay, and each of these fibers you see here, like for example this one, they end up forming these structures, okay, with very different properties depending on how you arrange them. If you put them together in a very high density, you get HDPE, which is used for applications like making a chair, like making the plastic drain cup and stuff. Okay, so they are made of the same material. Okay, pretty surprising. Now we will turn our attention to another plastic, okay, which is known as polypropylene. Okay, so polypropylene from the name, can you predict from which monomer is polypropylene made? polypropene. It's made from the alkene monomer called propene. And remember what we write inside the bracket is actually the monomer. And the whole thing, polyethylene is the polymer. Okay, so we can do the same thing here. What is inside this bracket? This is the monomer. And the whole thing, polypropene, we call it the polymer. Which means the monomer here is propene. So what can you learn from the name propene? How many carbon does propene have?
Five.
No, 5 is pent. 4 is filled. 2 is Eve. 3 is pro. Yeah, you should refer to that page. Do you still have that revision? Okay, we will have a test soon on this. Okay, so next
Okay. Next Monday. Okay.
next week.
Next.
Next week.
Next.
Okay.
Next.
Next double lesson.
No.
We have triple lesson this Friday. Of course, we will not bring this Friday. Yeah. From my past experience, I think having a single lesson for a test is not enough because it takes time for you to get seated for some students to join. Okay. So I think maybe arranging it in double lesson makes more sense. Okay. So we have propene. Pro means 3 carbon. What does alkene mean? What is the general formula of alkene? CnH2n. CnH2n. So let's put it together. When you put N to be 3 into CnH2n, what will the formula become?
C3H6.
C3H6. Okay, so you can write C3H6, and we'll draw it in the monomer section here. Okay, so and you should also do that. So C3H6, what does C3H6 look like? You have 3 carbons, and being an alkene means there is a double bond. So can you tell me how many hydrogens there are on the first, the second, and the third carbon counted from the left? How many hydrogens?
2, 3.
The second carbon should have 2, yes. And the second carbon should have only 1 because it already has 3 bonds. Can you see that?
2, 1, 3.
Yeah, so 2, 1,
3.
2, 1, 3. So make sure you know why. The first carbon, because it already has, yeah, always form 4 bonds. So you just have to count how many carbon bonds it's bonded to right now. So if there are 2 atoms, the first carbon is bonded. If there are 2 bonds already, you will have 2 hydrogens left. If you have 3 bonds already for the second carbon, there will be 1 hydrogen left. And for the last carbon, because it currently has only 1 bond, it means there are 3 hydrogens, right? Yeah. And then we have to turn this into this shape, into a molecule with this shape, with CC double bond at the center. So can you tell me,
General.
if I have to draw the C double bond at the center, what are the 4 groups positioned on the top left, top right, bottom left, bottom right? HH for the top left, bottom left,
C.
and what about top right?
C.
That would just be an H, top right, okay? And bottom right will be
CH3.
CH3. So we'll condense this group as CH3. Do you see what I'm doing? We have to put the C double bond front and center. And we identify the 4 groups at the periphery, at the corners. So sometimes it will mean condensing groups into one. Like in this case, of course you can keep writing CH3 like that. That's what I mean is something like this. But because this is so complicated structure, so we will sometimes just condense it as CH3. You can of course do that. Okay. Now, after we have found the monomers, does anyone remember what are the 3 modifications we need to make? We discussed this yesterday. To the monomer structure before we can draw the polymer. We add a bracket.
And
the
2 bonds on the side. One more modification.
N.
And then there is one last modification is to change the CC double bond into
Single bond.
single bond. So can you draw that now? You have CC, and you have to add 2 new bonds on the side and a bracket and an N and straighten up the other four groups. Okay. You see the four groups, they did not change at all in the reaction. The only thing that has changed is the double bond in the process, okay, and also the two side bonds on the side. So this is the polymer. We call this polyprotein, okay. The reactions of forming alkene, polyalkene. From alkene we call it addition polymerization. So do you all see polyprotein?
Yes.
How polypropene is formed? Yes. So what are some properties of polypropene that you need to know? So unlike polyethylene, which we have two different types of, polypropene we have just one type, but polypropene itself is harder than polyethylene. Does anyone know why? Let me put down the question here first.
The structure.
In terms of the structure, yes, it has something to do with structure. Can you elaborate a bit more? Put down the question first. Explain why objects made of polypropene is harder than those made of polyethylene. Well, I'll show you something. This is the polymer. What the polymer look like for PE and PP. For PE, you have something that look like this. Let me copy this 2 times. Okay, you have H. And polypropene has something that looks like this. Which has a larger molecular size? PP. Do you remember learning about intermolecular force?
More surface area.
It's not covalent bond, not density, but it's the
Stronger
intermolecular force. Intermolecular force depends on the size of the molecule. The bigger the molecule, the stronger the intermolecular force, the more tightly the molecules are held together. So this will mean it is harder to melt these structures, okay, made from polypropene than those made from polyethylene. So if you have, let's say this long rod represents polyethylene. Polyethylene chains, they interact with one another by intermolecular force, okay. Polypropene also interact with each other through intermolecular forces. But the intermolecular forces found between polypropene is much stronger than those found between polyethylene. That's because you can write down 3 points in here. Point number 1, polypropene has larger molecules. So it has larger molecules than polyethylene. So what? So the intermolecular force will be stronger in polypropene than in polyethylene. So intermolecular forces, what are some examples of intermolecular force? Have you heard of Van der Waals force? Van der Waals force, okay. So Van der Waals force is stronger in PP than in PE. So this is why objects, okay, made from polypropene, they are harder, okay, they are tougher. So therefore PP is harder due to the stronger intermolecular force than polyethylene. Is that clear? Okay? Right, so different plastics, we use them for different purpose. Okay, so polypropene is hard enough to be used to make a food container. Okay, a food container. So next up we have other plastics. Okay, this is just as important. Polyvinyl chloride. Okay, maybe I'll put this on the next page. So PVC. Okay, maybe you've heard of PVC before. So polyvinyl chloride.
Water pipes.
Yeah, water pipes, PVC. Yeah, so PVC. But actually the name vinyl chloride is a nickname for another compound, chloroethene. Okay, so put this down. Vinyl chloride. Does anyone know what a vinyl disc is?
Yes.
Yeah, if you know, you're exposing your age. Okay, you're old. You're old. Okay, you know those vinyl discs are this kind of thing. You put on a player, there is like a needle for you to put on the disc. Yeah, these are vinyl discs. They are made from like a similar compound, vinyl chloride. So vinyl chloride means chloroethene. So can you draw chloroethene for me? remember this is the prefix. Prefix tells you whether they are side groups, whether they are like halogens. If tells you how long the main chain is. In,
Two.
which is the suffix, yeah, so 2 carbons, here 2 carbons. The suffix tells you whether it has any functional group. So can you analyze the name chloroethene and show me what the monomer look like?
Is it this?
So the monomer is chloroethene.
Yes, I think so.
So draw out chloroethene first. So like we saw, chloro means there is which halogen present? Chlorine, there is a Cl halogen present, okay? And then we have the root. Root of E means there are 2 carbon. Yeah, there are 2 carbon, okay, there are 2. And the suffix in tells you that it is an alkene. What's the general formula of alkene?
Double bond.
General formula, not the functional group.
CNH2N.
2N, okay? So that means we now can draw 2 carbons connected by a double bond, and then there should be a Cl somewhere, okay? Anywhere will do. You can put Cl at any of these 4 corners, okay? I will just put it here. You can put it at any corner. That will be the same structure, okay? So then the remaining atoms must be H. So this is chloroethene. And can you put this structure in here and show me what the polymer looks like after undergoing addition polymerization? Remember the 3 changes you need to make. Number 1, change the double bond into single bond. Number 2, add a
2 bonds.
add 2 more bonds and put a bracket on the outside and an and, okay? Yeah, you need to draw it. And if you don't draw it out, you don't remember. So you have H, HCl, and then an N. Okay, so don't forget to put N times in here. Yeah, which I think I forgot on here. So we have N times. So you have N times ethene becoming polyethene. And here we have N times chloroethene becoming polychloroethene or polyvinyl chloride. So you can also write down the other name, polychloroethene. So PVC, okay, there are 2 types, just like there are 2 types of polyethene. So there are 2 types of PVC. One is known as the plasticized type. The other is the unplasticized. So we have plasticized. You can spell this as S, doesn't matter. Okay, I like to spell this with a C in this position. So plasticized PVC and unplasticized PVC. So plasticized PVC means there is something called plasticizer added. Yeah, plasticizer, as the name implies, it is something that will make something more plasticky. Okay, by making something more plasticky, we mean it makes it more flexible and more plastic-like. Just look at your rubber. Okay, it's more like plastic-like. But then when you do not add any plasticizer into PVC, it will be very rigid. Okay, very rigid. So you can write down plasticizer is added when you say you have plasticized PVC. And unplasticized PVC, of course, will mean plasticizer is not added. So let's see what the plasticizer will do to the PVC. First, you can write down this is softer. So therefore, it is useful for making what? Like garden hose. You know, garden hose has to be flexible, right? It cannot be a very rigid long rod, right? So useful as garden hose. But then the unplasticized PVC, they are harder, which can be useful in applications like water pipes. You know, water pipes shouldn't deform, right? Yeah. Imagine what happens when the weather changes. If it deforms very easily, then maybe you will also have a leakage very easily. So harder, so useful as water pipes. So water pipes. So let's see what the plasticizers do to the structure of the polymer. So can you draw this below? So explain with a diagram. Okay, with a diagram how adding plasticizer affects, so how adding plasticizer affects the hardness of PVC. So affects the hardness or rigidity of PVC. So this is the answer. First, let me draw out this polymer chain first. Remember, if this is PVC, so if this is PVC here, that means we have a very long chain of PVC like in the plastic. And we can simplify this into a single like a rod, like that. Okay, so let's simplify this into a rod shape like thing. When you have no plasticizers added, okay, maybe to keep things consistent, I'll write down or draw what plasticized PVC look like first. So plasticized PVC will look like this. Between chains of PVC, there are these molecules called PVC added. And because of the addition of the plasticizer, can the PVC chain come as close together? Can they come very close together, those black rods? No, because there is something orange in between, sticking in between. Because of the orange thing, the black PVC molecule, they cannot come very close to one another. So this is the PVC polymer. However, what happens if we do not add any plasticizer? Well, if we do not add any plasticizer, the PVC polymer, they can come really closely together. So that means, in which case, can there be stronger intermolecular force between the polymer? Is it when we have a plasticizer, or is it when we have no plasticizer? No plasticizer, correct. So can you indicate the strength of intermolecular force here? So with plasticizer, okay, so with plasticizer added, what will happen? So this is point number one. The PVC molecule, okay, PVC polymer chain cannot come as close together. So cannot come as close. And what is the consequence? Number three, the strength of intermolecular force decrease. The purple thing represents the intermolecular force. Okay, so the strength of intermolecular force decrease, which explains why it is softer. You know, when things are held less tightly together, it's softer, right? It's easier to deform the structure. Which is why if you make a garden hose out of plasticized PVC, you can bend it around pretty easily. Okay, so you can bend it around pretty easily because the intermolecular force is not strong. Okay, what about on the right? If we do not add any plasticizer, so I can just flip this around and it should make sense. Okay, so without plasticizer, PVC polymer chain can come very close, okay, together. So can come very close together. That means the intermolecular force strength can be pretty strong. Okay, so it can be pretty strong between these molecules. And if these are very strong intermolecular force, it makes them harder. Okay, harder to deform. So this is why in those pipes, so this is water pipe made out of PVC, we do not want to add any plasticizer in, and it will stay pretty rigid. Okay, and it will last very long because plastics, they are made to last. Okay, so we have, do you understand the argument here? Okay, and also why there is a difference in the property between plasticized PVC and unplasticized PVC.
Sir, how are plasticizers added?
Oh, how are plasticizers added? Actually, plasticizers are added to many things, including the bottle, okay, for bottle feeding babies in the past. And researchers have found that these plasticizers, they will disrupt your hormonal balance. For example, some babies, not baby, like the girls, okay, they reach sexual maturity very, very early because of the influence of these plasticizers. In the body, the plasticizer behave like the female sex hormone, which is why we need to ban it from those products for bottle feeding babies and stuff. And we are trying to find other, a better type of plasticizer to add into plastic. Obviously, we can't live without plasticizer because without them, well, you cannot make useful things like garden hose. But then, because we also know the side effects of adding certain types of plasticizer, like it will affect the girls in particular. Yeah, so we tend not to use it as often. In fact, we should phase out plastic altogether. Yeah, it's not about choosing this type of plastic or that type of plastic. We should not use plastic at all and resort to other more environmentally friendly material. But still, in this unit, we need to learn about what makes certain type of plastic useful for certain applications, even though we actually don't want them to last, especially in the lab field. Next up, we have another plastic that is also very important in life, and you must have used it before. It's polystyrene, or
Styrofoam.
PS. Yes, have you heard of styrofoam?
Yes.
Yes, styrofoam. This is where the word sty come from, okay? So polystyrene, its short form is PS. So that means this is the monomer again. And polystyrene being the polymer. Okay, so you have polystyrene made from the monomer styrene. Now, I want you all to show me the polymer. Okay? If I tell you what the monomer is. This is what the monomer looks like. It looks kind of scary. Okay, it has a hexagon here. And then you have some H's on the side. Do you remember what this hexagon with 3 lines inside mean? Benzene. Yes, very good. So that's a benzene ring. Remember compounds with a benzene ring, what do we describe them as? Do we describe them as aliphatic or aromatic? Aromatic, okay. This we mentioned way back. Let me see if I still remember where I put it. I think I put it somewhere, like in here, like almost 20 pages ago. But if I remember where it is, I'll show you, okay? Yeah, so this is the aromatic compound, you see. Do you remember this hexagonal ring? It's not the first time you saw it, okay, unless you have missed that lesson, okay? So these are aromatic compounds, okay? They are things with the benzene ring. Oh, we are here. So can you just put down this thing that looks like a sad face? It is actually C6H5. It looks kind of sad to me, okay? You have carbon here. At the corners, these are where you will find carbons. You will find 6 carbons. But why are there only 5 hydrogen? That's because only these positions can have hydrogen. The 6th position, this one, it is connected to the carbon. So therefore there is no hydrogen at that position. So it should make sense why this group is C6H5. Okay, so this is C6H5. Don't write C6H6. Okay, and then what? Can you turn this into the polymer for me? Okay, let's turn this into the polymer on the right. Oh, what do those lines mean? Actually, we are just being lazy in chemistry. Okay, to draw it properly, you should show the carbon. And we are showing 3 bonds in this position. Why can't we draw something like this? Why must those 3 bonds be arranged in this alternative manner? That's because carbon can only form 4 bonds. Think about what happens if you draw something silly like this. If you draw it like this, what is wrong? How many bonds is these carbon forming? Just look at this carbon. 5. That is forbidden. Okay, that is not allowed in chemistry. So this is why we are not drawing those 3 lines randomly. They have to be arranged like in this alternative manner to ensure that carbon form 4 bonds. Yeah, very nice question. Okay, so can you put down the actual structure of this? Yeah, it actually looks like this, but because we are feeling lazy, we will just not write out the carbon atom. Yeah, we'll just connect them together. We will not show the hydrogen. Yeah, so can you put down C and H's are not shown. Okay, so C and H's are not shown. Okay, for clarity. Right, so therefore, this is what it means. Now, tell me how you would convert this into the polymer. What are the modifications you need to make? Change CC double into single and add 2 new bonds and a bracket and an and. Don't forget to write n times next to the monomer, and then just straighten up the bonds. And oh, here, this is where you need to be careful. Don't draw something like this. What is wrong with this structure? If you draw it like this, is the carbon connected to any of those carbon there?
No.
No. If you write something like this, it's similar to writing something like this. It's similar to drawing something like this to me. And you know, I don't even know what this is. Okay, this is not H2O. Whenever you draw a bond, it must be drawn between atoms, right? So this is why when you draw the benzene ring, you cannot draw it like that, as it doesn't make sense at all. You have to draw it with the carbons, like a bonded to a carbon in the benzene ring. You get what I'm saying? Okay. Yeah. So that's the benzene structure. Maybe I'll keep this structure and then put a big. Okay. We'll pick up from here, and I'll let you know about the retest result. And we will have the test soon on organic. Please do revision on that. Prefix, root, and suffix page. You are not allowed to use that page in the exam. Okay. And you can, but you will be assessed on the application of that. Okay. Right. So I'll note this on the full custom.